Any number of the form a plus bi, where a and b are real and I is equal to square root of -1, is called a complex number. So, just to go into it more, if we write z equals a plus bi, where a and b are real, then the a is the real part. The b is called the imaginary part. And we can write re bracket z of that z, that complex number, will represent the a, and im bracket z of the complex number will represent the b. The complex number a plus bi has a complex conjugate called a minus bi. The idea here is that when you multiply them together, the i's will disappear, so that we'd get a squared, we'd get minus abi, we would get positive abi, and then we would get minus bi squared. So that the ABI's then are disappeared. The I squared is -1, which results in a squared plus b. B squared. That's why we have complex conjugates. It's similar to if we were factoring a squared minus b squared, we would get a minus b, a plus b. So this is the Argand plane. Looks very familiar, doesn't it? We've got numbers coming up to 5 here. Obviously it goes off to infinity. We've got negative numbers here. We've got, oh, this looks a little different. We've got I, 2i, 3i, 4i, 5i in what we would call the y direction. And we got down to -5i in the negative y direction. Though we don't call them x and y on the Argand plane, we actually will call them the real versus imaginary. RE and IM. We've got 4 different examples of how to graph on this grid. Our first example is this value right here, which is just 1. Okay, this would be if z, we'll call it z1, it's our first point, equals 1. You notice it could be written as 1 plus 0i, so it's 1 in the real, 0 in the imaginary direction. Our second point, we'll take this 3i. It could be written as 0 plus 3i. So, just like plotting the point 0, 3 in an xy plane, 0 plus 3i is plotted as x is 0, y is 3. So 0 in the real, 3i in the imaginary. We'll pick up 3 plus 2i as our third point. And so 3 plus 2i is plotted 3 in the real, 2i in the imaginary. And our last one is -4 minus 5i, which represents -4 in the real and down 5i in the imaginary direction.
Let's graph the complex number 2 plus 3i, which we're calling z1. So 2 plus 3i would be 2 in the real, 3i in the imaginary. So right there. Now what I'm going to do is I'm going to take and draw a vector from the origin to that point. The vector can be drawn from the origin to any point. So there it is, a vector. So what we do a lot of times is we represent the complex number 2 plus 3i, and we will write it as a vector 2, 3. We can see in this diagram is we have a complex number p of xy, which would represent here x in the real, y in the imaginary. The vector from O to p is xy, and it would represent x plus yi. Since complex numbers are really vectors, we can then do any operations with complex numbers the same as we would with any vectors. So for instance, if we have the following question, given z1 is 2 plus 3i and z2 is negative 3 plus 4i, and we wanted to calculate the summation, so z1 plus z2. So what we could do is start with the first complex number, 2 plus 3i, and we could write it as a vector. So 2 plus 3i, like so, 2 plus 3i. And the second one would be negative 3 plus 4i. Now, if we were adding vectors, what we would do is triangle law of addition, which means head to tail. So if I'm going negative 3 plus 4i, we're going to the left 3 and up 4i. So if I were to graph it, negative 3 plus 4i would go there. And so then there's the parallel vector or parallel complex number in this case. So what's our resultant? I'm just going to take this one away. What's our resultant or our solution? Is this vector here, which would represent, well, what is its complex number? It would be minus 1 and up, if you count it, 7i. Now, could you see a quicker way of doing that? As we know with algebraic vectors, we can just add the components. So it would be as if it was 2, 3 plus negative 3, 4. What does that give us? It gives us negative 1, 7. What a surprise. Negative 1 plus 7i. In other words, if you're adding these two complex numbers, all we have to do is add the components. 2 plus negative 3 is negative 1. 3i plus 4i is 7i. So what about subtraction? What if we did z1 minus z2? So z1, again, 2 plus 3i. So let's graph 2 plus 3i. There it is. And now we're going to subtract z2. So subtract negative 3 plus 4i. So here's negative 3 plus 4i. But just like in vectors, complex numbers works the same way. That negative sign is going to change all those signs. So negative 3 plus 4i would actually, just like in vectors, a negative vector become, well, it would be 3 minus 4i, as my red vector here represents. 3 minus 4i. So what I'm looking for now is completing the triangle between 2 plus 3i and 3 minus 4i. That gives us a resultant of 5 minus I, as is shown there. So again, that would be 5 minus I. Now how could we really do that? We could have 2 plus 3i minus negative 3 plus 4i. We're going to subtract, so we get 2 plus 3i plus 3 minus 4i, which works out to be 5 minus I. We could use the vector method as well with it, but what we're really doing is we're collecting the like terms. So in other words, we're collecting the real numbers and we're collecting the imaginary numbers. The next operation we want to perform with complex numbers is called the modulus. And the modulus is really the same thing as the magnitude of a vector. Just to recap, a complex number, AB, represented by z equals a plus bi, looks as in this following diagram. So it's a vector from O to that point, AB. Now, it's a vector. So we represent vectors, the magnitude of a vector, with the magnitude of a vector A. Notice it's the exact same symbol as what we're going to represent modulus. This represents modulus. So if we know the magnitude of for a vector that goes to the point AB, we actually do know the modulus of a complex number z, which also has the point AB. A plus BI. So what is it? Well, it's going to be that Pythagorean relationship. A squared plus B squared, and the square root of that. The last thing I want to talk about with complex numbers in this video is the argument of a complex number. So if we look at this vector here, we've got the vector from O to the point AP, and this angle theta is the angle that the vector makes with the real number axis. And that's what we're talking about when we talk about the argument. The argument of z, also written as just the argument of z, is that angle theta. The angle the complex number makes with the real axis. So how do we find theta? Well, it's in a right angle triangle. So what we do is figure out what we got. For theta, we've got the opposite over adjacent, so that's the tangent of theta would be the opposite side, B, or the adjacent side, A. Now, as we know, there's an infinite number of solutions to theta, but what we do is we always take theta to be between negative pi is less than equal to theta, which is less than equal to pi. This is our first of 5 different examples that we're going to be looking at. And this first one here says to find the modulus and argument of 2 minus 2i. So let's start off with the modulus. So the modulus of 2 minus 2i is going to be, if you remember, it's like the magnitude of a vector. So our vector is 2, negative 2. So it's going to be 2 squared plus negative 2 squared. Now, a lot of people may try to throw in an I, but it's not that at all. Just as a recap, the magnitude of A plus BI is the square root of A squared plus B squared. There's no I involved. The I just represents like the Y that it's on, the Y axis. Now, so that gives us what as an answer? Root 4 plus 4 is root 8. So that works out to be 2 root 2. Now to find the argument of this value, so the argument of 2 minus 2i, then what we're looking for is that angle theta that it makes with the real number axis. So just to recap, that's the tangent of theta is your b over your a, which in this case would be negative 2 over 2, which is negative 1. Now just remember, 2 minus 2i, 2 minus 2i is in this quadrant. So we're talking about by Cast's rule, tangent should be negative, but we're in the 4th quadrant. So we want, remember, from pi to negative pi. So we're in this range here. So we're going to write this as a negative angle. So let's take the positive value of it. So that's 1. So that's, where is the tangent 1? So let's just draw special triangles again. This is our 45-degree triangle. Remember, it's 1, 1, root 2. So wherever tangent is 1, we're talking about a 45-degree angle, or in this case, pi over 4. So this angle here is pi over 4. We want the negative. So theta is the negative of pi over 4. This is our second example. If z is 2 plus I and w is negative 1 plus 3i, we want to find the magnitude of z times the magnitude of w. So that's just the magnitude of z, which is, again, let's take a look at z. Z is 2 plus I. That's 2 plus 1i, or 2 squared plus 1 squared for the magnitude, which works out to be the root of 5. Again, there is no I in that magnitude. The magnitude of w would be the square root of my component, negative 1 squared plus 3 squared. What's that work out to be? 1 plus 9 is root 10. So the magnitude of z times the magnitude of w is root 5 times the root of 10, which is equal to the root of 50, which works out to be 5 root 2.
Our third example is a proof. And in this proof, what we're going to try to do is prove that the magnitude of z1, z2 is the same as the magnitude of z1 times the magnitude of z2. Now in the previous example, we looked at a couple complex numbers, and we found the magnitude of the first one times the magnitude of the second one. We could go back and show that it's equal to the magnitude of the multiplication of those two complex numbers. But that wouldn't be good enough to prove this is always true. To prove it's always true, we have to show it's true for all complex numbers. So for doing that, what we're going to do is we're going to start with some generic complex numbers. So let's introduce, or let, z1 equal a plus bi, and z2 to equal x plus yi. So we're going to multiply them together, z1 times z2. Let's see, what do we get? We get a times x, we get a plus yi, we get b xi, and we would get plus byi squared. Now rewritten, now remember this I squared is negative 1, so that'll go to the real side. So in the real number set portion of this complex number, z1, z2, we'll have ax minus by, and then in the imaginary we'll have ay plus bx. We'll put that in brackets, I. So what's the magnitude of z1, z2? Well, the magnitude then would be ax minus by all squared plus the imaginary portion ay plus bx all squared. Now I don't really want to expand that out, so I'm just going to hold off. How about the magnitude of z1? That would be a squared plus b squared. How about the magnitude of z2? That would be x squared plus y squared. So the magnitude of z1 times the magnitude of z2, when I'm saying magnitude, I should be saying modulus, is the root of a squared plus b squared times the root of x squared plus y squared. Ugly. Not what I've got here, is it? So let's see what we can do. We would put that all under the same root sign. So that would work out to be a squared plus b squared times x squared plus y squared underneath the root. And if we were to expand it, we would get a squared x squared plus an a squared y squared plus a b squared x squared plus a b squared y squared. I'm still not convinced that that's the same thing. Well, I think what we'll have to do, we'll have to expand this out. So the square root of, I would have a squared x squared. I would have a minus abxy. And I would have two of those. Plus a b squared y squared. Now as I keep going here with the second bracket, I would have a plus a squared y squared. And there in this case I would have 2 abxy. And then finally a plus b squared x squared. You notice what happens, of course, is these guys will cancel out, and I'll be ended up with what I had on the right hand side. Really, we've got a left side versus right side situation. I didn't really set it up that way, but I could have. A left side versus a right side, and our identity. The method that we solve identities. But there we go. We've got it. Do the same thing. Slightly different order. This is our fourth and probably hardest example that we're going to do in this video. And it's asking us to find the modulus of z. And what we're given is that the modulus of z plus 9 is equal to 3 times the modulus of z plus 1. And I've put this part up here at the top. It's going to help us solve this equation. In it, it says that the modulus of z squared is equal to z times its conjugate. Why is that true? Well, if z is a plus bi, then its conjugate is a minus bi. So that if I expand that out, I get a squared, the middle terms cancel out, and I get minus b squared I squared. Now, of course, I squared is negative 1, so that'll make that positive, which is a squared plus b squared, which, of course, is the modulus of z squared. We're going to use this fact to solve this equation, solve for the modulus of z. So let's start with our equation. And we're going to square it. And I'm going to just do a little bit of housework here and make it look a little neater, because this 3 has to be squared. And this is where I can use this information. So the modulus of z squared is z times its conjugate. So the modulus of z plus 9 squared is going to be z plus 9 times z plus 9's conjugate. The modulus, this will then be 9 times the complex number z plus 1 times its conjugate. Now this is a good time to look at something like z plus 9, the conjugate. Well, let's let z be a plus bi plus 9. And we're going to try to find its conjugate. Now the a plus 9 are real numbers, so let's kind of group them together. And then the conjugate, of course, we change the imaginary to be its opposite sign. So a plus 9 is not going to change, but the bi is going to become minus bi. So that's what the conjugate put in. And if I rearrange that, that becomes a minus bi plus 9. Well, what's a minus bi? Well, isn't it the conjugate of z? So this becomes the conjugate of z plus 9. So I can change this, and I forgot the conjugate sign. So I can change this right here to be the conjugate of z plus 9. And similarly, I can do the same for the right side. So that becomes the conjugate of z plus 1. Now, as a side note, what happens if I've got z minus I and find its conjugate? Well, same thing. I'm going to let z be a plus bi. The I, the minus 1, would then go with the i's. So that would be minus 1 I. I would then take its conjugate. Don't forget my conjugates here. That's what I'm doing. The conjugate then would be a, and that would be now minus b minus 1 I. If I were to expand that out, that would be a minus bi plus I. So in other words, what do I get here? I get the conjugate of z, and then the conjugate of that I. In other words, see how that one did change and this case as well, and that's because it's the imaginary portion. So the imaginary portion is going to change. But as we saw in these two cases, the real portion does not change when you take the conjugate. So let's focus back on our equation. So I'm going to expand this out. I'm going to get z times z conjugate. I'm going to get a plus 9z. I'm going to get a plus 9z conjugate, and then a plus 81. As I do the right side, I'm going to multiply it by 9. So I'm going to get to 9z times z conjugate. I'm going to get a plus 9z. I'm going to get a plus 9z conjugate. And then I'm going to finally get a plus 9. So as I collect like terms, I'm going to get an 8z conjugate. I'm going to get a 9z's are going to cancel off. 9z conjugates are going to cancel off. I'm going to bring this 9 over here, so that becomes 72. I can then divide by 8, so I get 9 is equal to z conjugate. And of course, come back to this original part here. Z conjugate is the magnitude, or the modulus of z squared. So that's going to make our final answer. The modulus of z is 3. That was a tough one. This is our last example, and what we're asked to do is to find the transformation that would move a complex number z to be negative z. So we're going to start with z being a plus bi. And then negative z would be multiplying z by negative, so negative a minus bi. So that's taking the point that would be in this first quadrant. So I'm just going to make it up. Let's say it was 3, 4. And it would move it to be negative 3, negative 4 in that second quadrant, or in the third quadrant. So what that rotation is pi, or 180 degrees. So rotation of pi radians. What would happen, let's just draw a line here. What would it be to travel to take z to iz? Well, again, let's start with z to be a plus bi. Iz, so we're going to multiply everything by I. That would now become ai plus bi squared. So bi squared would become negative b plus ai. You can see what happens is if I took 3, 4, it would now switch into, the b's would switch and become a negative, so negative 4, and the a would be 3, so it would switch over onto that range. So that's a rotation from the first quadrant into the second quadrant, and that is a rotation of 90 degrees. Alright, time to go. Get out. Come on, go, 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 go. That's better.